Microorganisms in nature drive biogeochemical cycles of carbon, nitrogen, phosphorus, sulfur, and many other elements. We will elucidate here these cycles and how we can harness them in the engineering systems of wastewater treatment plants. We will look specifically at the carbon, nitrogen, sulfur, iron, and phosphorus cycles that are relevant for BNR and anaerobic digesters. Globally, microorganisms provide important environmental services for nature, wastewater treatment, and environmental biotechnologies in general. It is important to understand their physiology, how they shape their niches along environmental gradients, and what are the main factors that select for them. Biological wastewater treatment consists of harnessing microorganisms and their metabolisms in engineered boundaries for nutrient removal. The main guilds involved in BNR relate to the key cycles of the carbon, nitrogen, phosphorus nutrients, among others. We'll see that there are a lot of interactions between the cycles in nature and wastewater treatment plants. Let's start with the carbon cycle. On this graph, the oxidations are displayed in pink and the reductions in blue. Pathways with no apparent redox changes are displayed in black. Organic matter is often contained in waste and wastewater as complex polymers. They are so-called the XS fraction in environmental engineering. These polymers should be first hydrolyzed into dissolved monomers, SS for soluble substrates, that can be taken up and processed by microorganisms. Depending on the conditions, this soluble organic substrate can be either respired, aerobically or anaerobically by OHOs or DHOs. In the absence of any terminal electron acceptor, the soluble organics can be fermented into volatile fatty acids and other fermentation products. VFAs, like acetate, are often formed in long, flat, non-aerated sewer systems. They are also very good substrate for OHOs, THOs, PAOs, and GAOs. Several of them can store the VFAs intracellularly as polyhydroxyalkanoates. In anaerobic digesters, acetoclastic methanogens produce methane from VFA. This process is typically endothermic since driven by entropy. Methane can also be produced by hydrogenotrophic methanogens that use CO2 and H2 as electron donor and electron acceptor. This process is exothermic, liberating an important amount of heat. Methane can also be used as electron donor and carbon source by methanotrophs that will oxidize it into carbon dioxide. Carbon dioxide can be fixed by autotrophic microorganisms, like not only acetogens and photosynthetic microorganisms, but also nitrifiers or anamox, among many other autotrophs. Overall, the carbon cycle feeds several other nutrient cycles with either E-donors, E-acceptors, like CO2 is an electron acceptor, or carbon sources. Let's look at the nitrogen cycle. It is an important cycle for wastewater treatment plants and nature. New insights are frequently discovered. Organic nitrogen, like urea, should be first ammonified, like in the sewer system or in anaerobic tanks, into ammonium, or ammonia depending on the pH. Ammonium can be nitrified through hydroxylamine to nitrite and nitrate by nitrifiers, by the aerobic respirations of AOOs and NOOs. Recently, Comamox organisms have been shown to conduct a full nitrification of ammonium up to nitrite and nitrate. All nitrifications require dissolved oxygen. If oxygen is limiting, nitrification will be incomplete. In denitrification, in blue, nitrogen oxides are reduced sequentially from nitrate to nitrite to nitric oxide, nitrous oxide, and dinitrogen. Organic matter, or H2 or H2S, can serve as electron donors for the reduction of all these nitrogen oxides. If an electron donor is limiting, the denitrification pathway is incomplete, and greenhouse gas emissions of N2O can be emitted. By the way, N2O can also result from nitrification via chemical pathways. Anamox is an interesting pathway combining ammonium as electron donor and nitrite or nitric oxide as electron acceptor. This is displayed here in red and blue in this pathway. It goes through the formation of highly reactive intermediate, hydrazine, that is contained in a special organelle called anamoxosome to protect the anamox cells. The sulfur cycle is simple with oxidations from dihydrogen sulfide to hydrogen sulfide and elemental sulfur and sulfate. It is conducted by sulfur oxidizing bacteria. Sulfate can be reduced back to elemental sulfur, hydrogen sulfide, and dihydrogen sulfide by anaerobic respirations that necessitate a supply of electron donors like organic matter, among others. The iron cycle is relatively simple as well, with oxidations of iron 2 up to iron 3. Iron 3 easily precipitates as iron hydroxide, leading to an orange-red color of rust, such as seen in the Rio Tinto River in Spain. This precipitation process is accompanied by a strong decrease in pH. Soluble iron 3 can get reduced back to iron 2, either microbiologically or chemically. The phosphorus cycle is different from the typical oxidoreduction loops of the carbon, nitrogen, sulfur, and iron cycle. But we still speak about phosphorus cycling. PAO selection runs via the alternation of anaerobic, aerobic, or anoxic conditions depending on the availability of electron acceptors. Under anaerobic conditions, PAO stores acetate as PHA. To do this job, PAOs hydrolyze polyphosphate to gain energy for the VFA transport inside the cell. And the polymerization of PHAs is made using glycogen to gain reducing power. When an electron acceptor like oxygen or nitrogen oxides is available in the mixed liquor, PAO can grow from biomass on the stored PHAs. They replenish the polyphosphate pool and glycogen pool as well. Since PAO cells divide and multiply during growth, they effectively remove the phosphorus from the wastewater below the influent level. Polyphosphate ends up in the waste sludge that is purged out of the system with the purge. Different process configurations can be designed from labs to pilot on full scales by involving sequencing batch reactors under stir tank or bubble column configurations with flux or granules or flow-through systems. The importance is that the biomass can experience this alternation of anaerobic oxic condition or anaerobic anoxic conditions to select for PAOs, and that biomass is effectively purged out of the system to remove the biomass saturated with polyphosphate and maintain a proper sludge age. As main take-home messages, microorganisms drive biogeochemical cycles of nutrients that are harnessed for biological nutrient removal in wastewater treatment plants. The CNP cycles harbor major conversions by BNR microorganisms. The S and iron cycles can occur notably in sewer systems or anaerobic digesters. PAOs have an interesting metabolism alternating redox conditions to promote their resource cycling and their selection. Definitely a good BNR performance relies on a proper selection of microorganisms and the activation of their metabolism through microbial community engineering and microbial resource management.